Okay, so let's start. So this is our third talk on this session. The next pair is Erva and Yurtbaş. So please.
Hi and welcome everyone. Today Erva is going to present Martingales, and I'm excited to introduce Erva. He is an undergraduate student in Boğaziçi Mathematics department. I had the pleasure of mentoring her, and her passion to mathematics is very impressive. And also thanks for the organizers for arranging the program. So, Erva, stage is yours.
First, I want to thank all of the organizers and my mentor for all of the efforts. Today, I will talk about Martingale and some of its applications. Here is a sketch of my presentation. I will first talk about Martingale and filtrations, then go to Optinal Stoppin Theroerem, and give a good example. Then I will briefly introduce you some brand new topic. Martingale is first introduced by Levy, even if he didn't name it. Like all of the topics in probability, Martingale also used in gambling. So a Martingale is a fair game in which your expected gain at every step is equal. So super Martingale is an unbiased game where you tend to very likely to lose. A stochastic process Xn is called Martingale relative to Fn and P. F is a filtration here and P is a probability function. First, Xn is adapted to Fn. Second, expected value of Xn is finite. And last, the conditional expectation of Xn, which respect to filtration, is equal to Xn minus 1. If we change the equality in third condition with inequalities, we get super Martingale, like here, or sub Martingale. So, what is a filtration? A filtration is a non-decreasing sequence Fn of sub-sigma algebras of F. Fn represents our information available at time n. More information becomes available as time evolves, so filtrations are naturally non-decreasing. We say Xn is adapted to filtration Fn when Xn is Fn integrable, which models the fact that the sample part of the process up to time n must be available as time n. The natural filtration that we talk here is the special filtration Fn. That is the smallest filtration that Xn is adapted. So intuitively, this means we have no information, but the information about past n steps. I want to give an example. A random walk, most of you know about it. A random walk is a process with sequence random steps. In number line, you start from 0 and then go to the positive direction with probability q, or negative direction with probability 1 minus q. If q is equal to 1 over 2, then our random walk is a fair random walk. Then, as you see here, is a Martingale. So I want to go optional stopping theorem. A stopping time, or some say hitting time, for filtration Fn is a random variable t from omega to n. Here omega is our sample set. T is equal to n such that for all of the numbers less than n, our random variable is not in B, but Xn is in B. Here B is the Borel set. So intuitively again, T is the time that we stop the process. The measurability condition here implies that our decision to end the process depends only on our knowledge at time n. So let's define stop Martingale. T is here stopping time again. Xn t stop process. If n is less than t, then it changes with time Xn. But if n is greater than t, it is equal to x always. I can make an analogous from life. You may think this stop process as marrying, and examine you, your current partner, your girlfriend or your boyfriend. You may think that they will be your husband or your wife, and T is your wedding day. Until that day, it might be changed, but after wedding day, it doesn't change anymore. It is he or she is your husband or wife. So our stop process, X and T, is also a Martingale. Here I want to show this expectation, this conditional expectation is equal to 0. First, I want to get rid of this C. So I use indicator function, which turns out 1 or 0. With the linear stop expectation, I can take this indicator function out of expectation. And since xn is fn adaptable, I can get rid of expectation in here. And with the martingale, since it's a martingale, this expectation is equal to xn. So it is equal to 0. Then xn t is a martingale. I want to introduce some properties and some theorem to use it then later. Our property, H is a subalgebra of G, H is in G. Then this double expectation, double conditional expectation, is equal to this conditional expectation. In here, we simply get rid of the greater filtration because only the smallest filtration is important here. So, with this property, xn is a martingale. I want to take a look at expectation of xn. With our property, I can write xn like this. And I know this is equal to xn minus 1. With recursive calculations, I can get that expectation of x0. So all of the xn, the mean of xn is equal to expectation of x0. There is a convergence theorem. Just don't forget that because I will use this in proof. Y is Lebesgue measurable, and expectation of y is finite. And for all n, xn is dominated by y. Then, in here, I can take limit inside the expectation function. Okay. Assume xn is martingale for fn, and t is stopping time for that filtration. If one of the following conditions holds, we have expectation of xt is equal to expectation of x0. What is conditions? First, our stop martingale is limited by c, and t is finite. Second, the difference here is bounded by a constant, and the t is almost surely finite. To get this, we don't have to, hold both. We have to just one. Okay. I have said that random walk is a martingale. Let's say that we are starting from 0 and we are going to stop when we arrive at point 50. So this is a stopping time. And expected value of xt is 50 because this is where we stop. And expected value of x0 is 0, but they're not equal. This is because t is not bounded here. We can go far negative before arriving 50, so it is very important condition. Optional stopping theorem is also called Dupes optional sampling theorem for American probability series of 2. He implies that under these conditions, the expected value of martingale as a stop time is equal to initial expected value. On average, nothing can be achieved. Or some says cash always wins. So here's the proof. In first assumption, stop process is bounded. So in number 7, I can get this limit out of the expectation, and xm is martingale, I use it, and we get the equality. To deal with second case, then I want to bound my variable, this difference is equal to this sum. I know this is bounded by CT, and CT is expectation of CT is finite. So again, I use some negative. This expectation is equal to 0 because it's martingale. Then I do some calculations and I get the same equal. I want to give a good example. There is one more example, maybe you can sort for it. There is Gambler's rule problem for optional stopping theorem, but I don't want to talk about it today. I will talk about abracadabra problem. Imagine there is a monkey randomly types on keyboard one letter at the unit of time uniformly. What is the expected time monkey will write abracadabra? I do this with this word because it is very famous in papers, but you can change it with any finite words. So here's the idea. Again, there's bet $1 at each step that monkey will write upcoming letter at our main sequence, for example, R or A. If he guesses, he will get $26K. Otherwise, he'll lose all of his money. XM is the gain of our gambler. There is -1 because he will bet $1 at each step. And in this sum, the indicator function gives us the monkey how many times has written the word. And each time our gamblers get this value. But there is also a partial gain because there is, for example, Erva in here, there is A in here. For that repeats, our gamblers get a partial gain. So xm is equal to this. Xm -1, the gain at last step. Am is the gain of the gambler step, and our gamblers bet $1 again. I want to calculate this expectation. Xm -1 is fm -1 measurable, so I don't care about it a lot. I want to calculate this. Here, imagine we are here and we go to the next step here. If monkey writes R with possibility 1/26, our gambler get this. If our monkey starts sequence again with A, with probability 1/26, our gambler get this. But there can be other possibilities. Let's say monkey writes X. In this case, our gamblers lose all of his money with probability 24/26. So expectation of AM is equal to 1. If we integrate this our formula, we get that xm is a margin. Okay, to continue the problem, I want to use optional stopping theorem, but I want to show that our random variable is limited. If m-1 is less than t, then this difference is equal to n plus 1 minus 1. The maximum of this value is 20. Is this minus 1? So our random variable is limited. And in here, this is also a stop process. So there is no gain process to process. Okay, apply velocity. AXT is equal to AX0, which is 0. In here, this is the gain of our gambler, and this is the expectation of time. So expectation of time is equal to 26 or 11 plus 26 4 and 26. It's a very long time actually. Okay, let's continue with another application. Elephant random walk. I have introduced you random walk, and I have stressed that there is no importance of fast stop. But what if there was a jar with full of our previous steps, and every time that I will make another step, I take one of the previous step as sample path and use it and use the direction. So Günther Schutzberg has asked the same question and introduced a paper. he has examined the asymptotic behavior of reinforced random walk. So element starts at origin 0 and with probability Q go to the right or go to the left with probability. So this is the position of elephant. So Xn is the step. Alpha is a Radamacher distribution. It is either 1 or -1. Beta is uniformly distributed over this set. So we are choosing randomly from our draw. P is here our memory parameter. So actually we are using our sample with probability P or not using it with probability 1 minus P. Here's tedious calculations. I will just oversketch them. Here I am defining another variable, and n is this multiplicative formula. Here this is Euler's gamma function, and am I'm defining another random variable, and n is equal to an sn, and this is a martingale. All of our efforts here to proving this step, this process is a martingale, and using martingale convergence theorem to deduce the asymptotic behavior of walk. In papers, they define two main regimes, diffusive regimes with respect to value of P, critical regime, and diffusive regime. I won't go any further in this topic to not bore you, but you may read this paper. And David Williams' book is very good books in probabilistic martingales. I have told only about discrete martingales, but there is also continuous martingales. They are, if you're curious, you can check it. And Launcher book is also good. It is more. Thanks for listening.
So, any questions?